Hello everyone. Today's topic is RAID. Today's topic is RAID. RAID stands for Redundant Array of Inexpensive Disk. It's called RAID. So RAID uses multiple disks to build faster, bigger, and more reliable disk system. There are many levels of RAID, and we are going to introduce 4 different levels of RAID: RAID 0, RAID 1, RAID 4, and RAID 5. Of course, there are many different types of RAID. For example, RAID 10, RAID 10, or RAID 01, or RAID 6. But in this text, we're gonna cover just 4. RAID is a technique to use multiple disks as a single disk. So let's say there are 4 disks, and then uses them as a single disk. Then ideally, the capacity of this RAID system is, let's say each disk can contain B byte. Then total number of disks is 4. And then each disk can contain B bytes. Then the capacity of the 4-disk RAID system is 4 times 4 times B, for example. However, in this case, there comes a reliability problem. If one of them fails, then all the disk fails. So to improve the reliability, RAID introduces some kind of technique to improve the reliability of the RAID disk system. So based upon different techniques, the RAID level is determined, and in our explanation, we're going to evaluate the reliability of individual RAID level. And we're also going to evaluate this performance of individual RAID techniques for read and write operation. So first one is RAID level. In RAID, the number of disk, and this is called a single stripe. So in RAID, first you write the disk block in round robin fashion. For example, if you write 16 blocks, then the easiest way to distribute these blocks is in round robin fashion. Write the first block, block 0, to the first disk, and write the second block to disk 1, write the third block to disk 2, and write the third block for disk 3, and then comes back to the first block, and then write the blocks again: 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So this is, we write the blocks in round robin fashion, and this is called RAID level 0. This is the simplest form of the RAID. So in this approach, we spread the blocks across the disk in round robin fashion. So usually, this is called stripe, and so this is called single stripe. So for the RAID, if you write 4 blocks from 0 to 3, then you distribute these 4 blocks to each of the disk, the four disks. So in RAID system, for this particular type of RAID system, if you write 4 blocks, if you write 4 blocks from 0 to 3, then the time to write 4 blocks is the same as time to write a single block. That's the beauty of RAID, because you can write the data blocks into 4 disks in parallel. That's the advantage of employing a RAID system. Let's think about the effect of the device. In the previous slide, the RAID controller writes 1 block, and this is 1 block. There are 4 disks: disk 0, disk 1, disk 3, 2, 3, disk 4. 4th disk. So disk 0, 1, 2, 3. And we have written a block for each disk. So this is block 0, 1, 2, 3, and 4, 5, 6, and 7. So the chunk size is 1 block. In the previous slide, in RAID controller, we can adjust the size of the chunk. So we can make the chunk 1 block, 2 block, or even 8 block, for example. There is pros and cons of adjusting the chunk size. If the chunk size is small, then we can distribute a single file across the multiple disks. So we can introduce more interfile parallelism. However, when you read a single stripe, you have to read all the disks that participate the stripe. So when you read the block of stripe, then each disk has to position its head to the proper sector, introducing secant rotation delay. So when this chunk is small, then for read same number of to read the same amount of data block, for example, we are going to read 16 kilobyte, then you have to read 4 disks in parallel. In this case, you have to synchronize the secant disk rotation delay across the 4 disks, and the positioning time of reading those disks is governed by maximum of the positioning time. So the position time gets larger. On the other hand, if you use large chunks, for example, if you write 4 blocks at a time for each disk, then you will going to reduce the intraparallelism, which is not good. However, you will get the smaller positioning time. Let me give you an example of a bigger chunk size. This is RAID level 0, and the chunk size is 2 blocks. So we are writing 2 blocks each to each disk. Disk 0, disk 1, disk 2, and disk 3. So chunk size is 2 blocks. And then again, this writing 2 blocks to disk 0, writing 2 blocks disk 1, writing 2 blocks disk 2, and writing 2 blocks and disk 3. So this is striping with a bigger chunk size. Of course, if you let's consider a situation where we have to read block 0 and block 1. In the previous example here, we have to read 2 disks at a time. Block 0 from disk 0, block 1 from disk 1. So you have to synchronize the reading activity from the 2. But if you use larger chunk and block 0 and block 1 belongs to the same disk, then we can read just disk 0. So which one's faster? It depends on how long does it take to read 2 blocks. So determining the chunk size is quite a difficult issue. So let's look at the performance, reliability, and capacity of the RAID 0. So there are evaluate the capacity, reliability, and performance of the striping. So first approach is single request latency. So how much parallelism can exist during a single I/O operation. And second avenue is steady state throughput of the RAID. It's a read and write bandwidth basically. Let's consider the single disk average seek time is 7 milliseconds. This is and average rotational delay is 3 milliseconds, and average transfer rate is 50 megabytes per second. The transfer rate means that you fix the disk, so head does not move, and then when the head was fixed at a single location, you rotate the platter and draw the time to read the data blocks as fast as you can. That's what we call by transfer rate of the disk. And for a single disk performance, for sequential I/O, we assume that average sequential I/O size is 10 megabyte. And for random I/O, you assume that average I/O size is 10 kilobytes. So for time to the actual bandwidth, the effective bandwidth is the ratio between the amount of data and time to access those data. So amount of data is 10 megabytes. And for this disk, okay, time to read 10 megabytes corresponds to move the head to the desired track and rotate the platter to get the starting set underneath the disk head, and then just read it. So this is seek time, and this is rotational delay, and then we are reading 10 megabytes. So we are reading 50 megabytes for each second. So if you read 10 megabytes or write 10 megabytes, then you just simply divide it by 5. So it takes 1 second, and we divide it by 5. We get 200 milliseconds. So it takes 200 milliseconds to read 50 megabytes or write 50 megabytes. So the total time is 200 milliseconds in the denominator side. So eventually we get 447.62 megabytes per second bandwidth for sequential I/O. For random read, the situation is entirely different. The amount of data is 10 kilobyte, and positioning time remains the same, 7 plus 3. This is seek time and rotation delay. However, it takes 0.195 second to read 10 kilobytes. This is derived from 1050 megabytes per second transfer rate. If you compute this, then random I/O, random read or random write renders 0.98 megabytes per second. So there's a dramatic difference between sequential I/O bandwidth and random I/O bandwidth. Let's get back to our original business, RAID 0. If you perform random I/O, random write, or random read, then the total throughput corresponds to n times r. So this is r. And for sequential write, because you can perform sequential I/O in parallel to all disks, sequential write bandwidth and sequential read bandwidth corresponds to n times s. That's easy. So remember, there is s. The sequential bandwidth is s, and sequential random bandwidth is r. So we're gonna differentiate sequential read and sequential write and random read and random write in the later part of the presentation. There's a new technique called level 0. This is called also mirror. Every disk contains a mirror to another disk. So copy more than one each of the blended system, then the copy block is placed on a separate disk. This is to tolerate the disk failure. So if you write block 0, then there is mirror for disk 0. Disk 1 is mirror. And for disk 2, disk 3 is mirror. So every block has its redundant copy. So even though entire disk fails, or another disk fails, here the strap size is 4, so there are 4 disks in the RAID system. Even though half of the disk gets lost, this disk can survive. The concept is easy and the reliability is good, but it has its own price, the capacity and bandwidth. So capacity, the total capacity is n times b. The n means the number of disks in the RAID system, and b means the number of capacity of single disk. Normally, because there are n disks, the total capacity corresponds to n times b, but because in terms of disk mirroring, we copy every block to its not redundant copy, so actual capacity that is available to the user is half of what is offered by the disk system, n times b divided by 2. Reliability is good. If you're lucky and if half of the disks are, then RAID 1 still survive. That's for sure. And for RAID level 1, sequencer write, then you can write only to half of the disk. So the sequencer write bandwidth corresponds to n times s divided by 2. Sequencer read is the same, and because you can read sequentially from the large number of disks, but still you can read only from half of the disk. For random write, it's a similar. The random write performance corresponds to n times r divided by 2. But the interesting part is random read. Okay, if you read random blocks, and if you distribute those requests over multiple blocks, then if all those blocks are different, all in a single stripe, if you read different blocks, then the actual bandwidth of random read corresponds to the number of disk times the performance of a single random read. So it corresponds to n times r. The next topic is RAID level 4. So the price of RAID level 1 is very expensive. To increase the reliability, it reduces it wastes half of the disk capacity. That's problematic. So they introduced the concept called parity. So here there are 4 disks, disk 0 to disk 4. And we are using one of the disk as designate one of the disk as a parity disk. In this scenario, disk 4 is designated as a parity. Disk 4 contains the parity of all the blocks in the stripe. So here, parity 0 is block 0, 1, 2, and 3. So within a single stripe, the parity block contains the parity of rest of the blocks. In this case, there are 1, 2, 3, and 4. So 0, 1, 2, 3. So here, P0 is an exclusive OR of 4 blocks, 0, 1, 2, 3. Okay, this is RAID 4. In RAID 4, if one of the disks dies, for example, if the disk 1 crashes, then we can rebuild all these blocks, the rest of the blocks, using parity. So let me give you 4 disks, 0, 1, 2, 3, and 4. And disk 0 contains 0, disk 1 contains 0, disk 2 contains 1, disk 3 contains 1. And then disk 4 contains exclusive OR of those bits 0, 0, 1, and 1. Likewise, for this 4 disks, disk 0, 1, 2, and 3, it contains 0, 1, 0, and 0. And then, fourth disk, the parity bit contains exclusive OR of those bits. For example, let's say how we construct the crash disk. Let's say this block has been lost. Okay. Then the bit value of 0 can be reconstructed from rest of the blocks. 0, exclusive OR 1, exclusive OR 1, exclusive OR XOR of 0, 0, 1, and 1. The same things apply to the second disk. So this is how we reconstruct the parity block to reconstruct the lost disk. In RAID level 4, full stripe writes are the most efficient way. So there are 5 disks in a stripe, and you write 4 blocks at a time. Then that's the most efficient way of writing the blocks in RAID level 4. That's because when you write 4 blocks at a time, you compute parity without reading the parity from the disk. I'll explain later shortly. But full stripe write's the most efficient way in RAID level 4. Let's perform the analysis on RAID level 4. Capacity is n-1 times b. Sequential read performance and sequential write performance is the same. There are 5 disks, and this 4 is used as a parity disk. So there are 4 disks in total. For sequential operation read and write, we can read from this disk in parallel, and we cannot access disk 4 because we do not have any data in disk 4. It contains only parity. Sequential write, if you write full stripe write, if you write 4 blocks at a time, then we can fully utilize n-1 disk bandwidth effectively. But that's only for full stripe write. For random read is the same. There are n-1 disk, and we can read from those disks. So total bandwidth for random read will be n-1 times r. This space is left as a blank for random write. In RAID level 4, random write performance is problematic. For random write, there are 2 approaches. In parity update, first one is additive parity update, and second one is subtractive parity update. In additive parity update, you need to read all data blocks and compute update the block, and then compute the new parity and write the updated block and update parity. So let's consider these 4 disks. And this is parity disk, and you are going to update these blocks. And then you have to read all the blocks in the stripe and read all 3 and recompute the parity and then write it to the parity block. This is parity update. The problem of this parity update is the amount of data blocks you need to read depends on the number of disks on the stripe. It linearly increases with the number of disks in the stripe. So the problem is the scalability. So the solution to this problem is subtractive parity update. So in this approach, it reads the parity. It's only read the parity block. And then when you compute the new parity, it performs, let's say C is chunk. You want to update. And then there is C new. This is new chunk, contents of new chunk. And this is contents of the old chunk. And then this is old parity. So the new parity is computed as the exclusive OR of all these data blocks, and it becomes new. Then in using subtractive parity update, you do not have to read all the blocks in the stripe to update the parity. So this looks pretty reasonable approach, because in updating the parity, instead of reading all the disks that participate in the stripe, it updates only the new blocks, a new parity. So that's good approach. Okay. So for every random write, you have to read the parity and you have to write the parity. So let's consider this entire disk subsystem. And there comes lots of random writes at the same time. Then what is going to happen is this is parity. Then there's going to be bottleneck on the parity block, because for every random write, you have to read a parity block and update the parity and write it back to the parity block to its original location. And for every write, it requires two IO for the parity block, one for reading the parity and one for writing the parity. Okay, so one for reading the parity, one for writing the parity. So if random write performance was R, and then actual random write performance in rate level 4 corresponds to R divided by 2, because for each write, even though there are bunch of writes coming in, the access updates is bottlenecked by the writes parity update on the parity block. And for each write, it causes one read and one write. So the performance will be decreased into half. So this is what you call small write problem in rate level 4. They come up with a new idea, and they introduce a new concept of rate level 5. They rotate the parity. The small write problem is due to the bottleneck on the parity disk in rate level 4. So in rate level 5, instead of designating a single disk as a parity disk, it rotates the parity. So let me look at the example. Here, this is 5 disk. A single RAID consists of 5 disks from RAID disk 0 to disk 4. And then at the first try, disk 4 is parity. And second try, disk 3 is parity. For third try, disk 2 becomes parity. So when writing the disk block, the writing starts from disk 0, 0, 1, 2, 3. And in the next write, the writing starts disk 4. So the fourth block is written to disk 4, and fifth block is go to disk 0, sixth block goes to disk 6, and stuff like that. So as a result, the parity is distributed evenly across the all disk. This is a very interesting approach. Let's look at the actual performance contribution of this approach. Capacity is going to be the same. It's n-1 times b. Rate level 5 can survive single disk failure in this type. Sequential read and sequential write is the same as before. It's n-10 times s. Random read is the same. It's n times r. If you consider a rate level 4, the random read performance corresponds to n-1 times r, because only there is a single disk that has been designated parity disk, and we cannot save any blocks there. But here in RAID level 5, we rotate the parity, so all the disk blocks contains the data blocks. So random read corresponds to n times r. Okay, the last one is very interesting approach. In random write, a single disk can cause 4 IOs. Okay, to read and to write. So for writing a single block, let me draw a picture here. 1, 2, 3, 4. To write a single block, update a single block, we have to read this block. And then we have to update the matching parity for the same stripe. And then we update the data block and then compute new parity and then write it back. Okay, so this is the amount of IO that is generated by writing a single data block. Okay, so single write will cause 2 reads and 2 writes. Okay, so if you perform write operation randomly and there are a huge number of random writes coming in, then total amount of IO generated by these random writes corresponds to 4 times the amount of IOs generated by random write. Random. So if you sums them up, then total amount of IOs that has been created by random write operation is going to be 4 times the amount of write operations. Therefore, the AND disk has to handle the 4 times as many IOs as the number of writes in the system. So random write operation, the performance is going to be n times r divided 4. So this is summary. So capacity, the rate 0 is going to be n times b. This is, n divided by 2. This is n minus 1. n minus 1 is the same. Reliability, RAID 0 cannot survive any single disk failure. So the RAID 0 corrupts if any one single disk fails. And RAID 4 and 5, we can survive single disk failure. And in RAID minus 1, it can survive, and divide by 2 disk failure if it gets lucky. And for RAID level 0, let's look at the performance on each RAID level. For sequential read and sequential write, RAID level 0 renders n times s performance. For random read and write, it's going to be the same, n times r. Okay. For RAID level 1, because this is meter, so sequential read and write renders n divided by 2 times s. For random read, it's the same, n divided by n times r. For random write operation, it renders n divided by 2 times r. Okay. And for random RAID level 4 and RAID level 5, sequential operation is the same, n minus 1 times s. For random read operation, because only n minus 1 disk contains legitimate disk, the performance is going to be n minus 1 times r. On the other hand, for RAID level 5, all this contains a data block. So for random read operation, the performance is going to be n times r. For random write operation, RAID level 4 has small write problem, then performance is r divided by 2. This is very problematic. However, by rotating parity, RAID level 5 renders n divided by 4 times our performance. Read latency is the same for all levels. Is d, the time to read a single block. However, for write operation, for RAID 4 and 5, because it has to read the parity and update the parity, the time to write a single block, the latency to write a block is twice as long as its original latency to write the disk. This is the summary for RAIDs.